Benz. I got no love for these niggas. There's no need to be friends. They got me under surveillance. I swear somebody can tell them. No, there's no being sold. But I ain't the one selling. Don't wanna be another number. I got a bumper gang of weed to keep them going under. The federalists wanna see me dead. Niggas put prices on my head. Now I got $2 by my bed.
Hello and welcome to the practice problems video on the section entitled vector fields. Okay, so the first problem, number 1, we're going to do the following. Compute the vectors. So compute vectors assigned to the following points. We have point P equals 0, 1, 1. And then point Q is equal to 2, 1, 0. Okay? And then our given vector field is F equals xy, comma, z squared, comma, x. Okay, that's a y there. And then, okay, so this is all we're given. And basically, this is kind of just a simple introductory question. So at these points, these are two separate points, so we're going to evaluate the vectors assigned to each point by this vector field. So let's do point P first. So f of P is going to be f of 0, 1, 1, which, so this is our x, that's our y, and that's our z. And then when you plug them in, we get x times y, so 0 times 1, comma, z squared is 1 squared, and then x is 0. So this is going to turn out to be 0, 1, 0. Okay, so that is the vector assigned to point P. And then, likewise, we're going to do the same with Q. So we have f of 2, comma 1, comma 0. So again, x, y, z, it's an x. So this is going to equal x times y, so 2 times 1, 1, and then z squared, so that would be 0 squared, and then our x is 2. So in this case, 2, 0, 2 is the point assigned to Q. Alright, so now just graphically, this isn't necessary, the question doesn't ask for it, but it's always good to draw some sketches to see what things look like. So we have our x-axis here, our y-axis, 1, 2, 3, 4, 5, 6. That's our y-axis, and our z-axis is going to be 1, 2, 3, 4. Okay, so let's look at this. What do these actually represent? So at point P, so these two go together. So at point P, that's 0, 1, 1. So 0 in the x direction, 1 in the y direction, and 1 in the z direction. So this lies on the yz plane. So this is point P, and then the vector attached to it, so from here we're going to go 0 in the x direction, so nowhere in the x direction, 1 in the y direction, and then 0 in the z direction. So this vector is going to look like that. Okay, and this is point P again. So that's what that looks like. And then now let's look at Q. So now we have Q here, and the vector attached to it is 2, 0, 2. So 2, 1, 0, that means 2 in the x direction, 1 in the y direction, and 0 in the z direction. So that point Q is lying on the xy plane. And then we have the directions from there that the vector tells us is 2, 0, 2. So that means 2 more in the x direction, 0 in the y direction, and 2 up. So somewhere up here, like that. So this is where this vector is pointing. Okay, something like that. And this is Q. Okay, so that's what it would look like graphically. Alright, so next question. So now number 2. So for number 2, we're supposed to prove that, that the vector field F, which is given by yz, comma, xz, comma, y, is not conservative. Okay, so how are we going to do this? One pretty quick go-to method is to check the cross partials. And if any one of the cross partials is not fulfilled, like one of the equalities or the pairs is not fulfilled, then it automatically is not conservative. So let's try that. So what we can do is check cross partials. Check. Ooh, that was a weird C or an E. Looks like a C. Check cross partials. Okay, so let's start with df1 partial y, and then we'll compare that to df2 partial f2 with partial x. So let's see what those equal. So that gives us, on the left, we have d partial y, and then of yz, right? That's f1. So then we get that equals z, and then partial f2 partial x is going to be partial x of xz. So this also is going to equal z. So these are good. That one checks off. Now let's try the next pairing. So then we have partial f2 partial z, and then does this equal, and this should be, does this equal partial f3 partial y? Okay, let's see about this one. So we're going to take the partial with respect to z of f2, so that would be xz. So then this is going to equal x. And then we have the partial of y with respect to y of f3, which is just y. So that equals 1, which is, so as we can see here, x is not equal to 1. So x is not equal to 1. So the cross partials condition, we could say the following. So no, not, well, we could just say that vector field F is not conservative because the cross partials condition, and you can say either is violated or is not satisfied. Is not satisfied. Okay? Alright, so we just proved that our given vector field is not conservative. Okay, now on to the last question for this section. So number 3, we have, we're given the following vector field. F equals yz squared, comma, xz squared, comma, 2xyz. And we are told to find, okay, I should close that. Find a potential function, v of x comma y comma z. All right. So we're going to practice finding our potential function here. And so this I'm going to label f1. This is f2, f sub 2, and this is f sub 3. Okay? So this is our given. And we're finding the v of x, y, z. So the first, so for a potential function, the first component should look, well, all of the components should be, make up the gradient of v, right? So the first is partial v partial x, the next is partial v partial y, and the last is partial v partial z. Okay? So if we have this, then we have to say that this must match up with this, right? f1 and partial v partial x. So we're going to set that up. Partial v partial x should equal yz squared. So then what we'll do is integrate with respect to x on both sides, okay? And then on the left we have a v of x comma y comma z, and that's going to equal, since we're integrating with respect to x, the y's and z's are constant, so we can think of this as that, right, when we integrate, plus some function of y and z alone, some combination of them, because anything with a y and z in this case will disappear when we differentiate to get back to this. Okay, so this is a candidate for our potential function. So let's check some other ones, see what we get there. So let's do partial v, partial y now. So this is our second component, right? So now we're doing these ones, we're matching those up. So we get that this equals, or should equal, x times z squared. So if we integrate with respect to y on both sides, okay, and this is what we're going to get is another candidate function. So this is v of x, y, z equals, and again, we're going to get an x times z squared times a y plus some function of x and z alone. Okay, because this is considered a constant, right, in this integration here specifically. So this is another candidate, and then let's do the last one. We'll do the last pairing up over here. So this is going to be partial v, partial z equals, sorry, let me scoot that over a little bit. Okay, equals 2xyz, and if we integrate with respect to z, let's see what we get here. This one's a little bit more interesting because we actually have a z in the integrand. So x, y, z, and then if we integrate with respect to z, we're going to get x, y, z squared, plus some function of x and y alone. Okay, so these are our three candidate functions, and we just have to see what matches up, and make sure to include all of the different parts of each. Okay, so as you can see here, in the first one we have a y times z squared times an x. In the second one, we have the same thing, just in a different order. And in the third, we have the same thing. And then we have the extra, added on to the end functions, just in case we need them. But in this case, we do not need them, because there's nothing else that doesn't match, if that makes sense. So basically, what I'm trying to say is that if we made our potential function be x times y times z squared, plus another constant, like a number or something, we would be fine. And you can always go back and check, like I said, go back and check that partial v, partial x, so if we were to do that, we would get yz squared. So that should be our first component, which it is, up here. Good. And then we can check partial v, partial y, which should be our middle component, which is x times z squared, which it is, up here. And then lastly, our partial v, partial z. So if we did that, then we would get 2 times x, y, z, and that it gives us our third component. Okay? So this is our potential function for the given vector field. All right. That is all for this section, and I hope you'll join me for the next practice problems video.
Heart beating in my head swollen, thinking of the G's I be holding. Picture me rolling. Can you see me now?